Hi, my name is Mark Litterick. I'm going to present today a paper from colleagues Vance, Montesano and myself, entitled To Infinity and Beyond, Streaming Data Sequences in UVM. By way of introduction, let me talk a little bit about the background to this paper. Verification often requires us to generate continuous streams of low-level data, which can be primary or background stimulus. And as verification consultants, we get to work on a great variety of different projects, applications, different clients, and we observed many different solutions to this particular verification challenge. Some of these are somewhat inconsistent, ad hoc, others provide low performance or poor encapsulation. So in this paper we're going to present an elegant and pragmatic solution that's both flexible and well encapsulated and is basically in line with standard UVM practices. The solution here has evolved over time with exposure to these different projects at various clients. For the agenda, I'll first present the concept and context for the autonomous data streaming, describe then the sequencer and driver operation, and demonstrate in some detail the implementation for simple and slightly more advanced analog stimulus. And I'll also discuss digital stimulus, file-based stimulus, and implementation of internal driving. Now, in the context of this paper, streaming is a stimulus pattern, in particular where we take a single sequence item and that defines repetitive streams of low-level data values. These data values are not generally random, they have some pattern associated with them, and they could go on forever in the background. The driver operation is autonomous, insofar as the derived low-level values are generated by the driver independently based on the description passed through the sequence layers. The driver can run forever without any further intervention from the sequence libraries, but it can be interrupted at any time with new stimulus request when required. Let me talk a little bit about primary application of this approaches we're talking about here. It is primarily targeted at digital simulation of complex sensor SoCs and similar devices, where we care about the verification of the digital subsystem, but we also care about the validation of the whole system, including the integration of the analog models and the interaction. It's especially applicable to SoCs that contain real number analog models for the subcomponents. Now, these analog models are typically either dealing with external inputs such as RF or microwave antennas, maybe optical receivers, or embedded sensors that are sensing external influences such as temperature, pressure, acceleration, or internal currents and voltages. And typically we would have analog multiplexers and analog front-end processing, filtering, that kind of stuff in the loop. Ultimately, we expect, of course, the analog to digital converters to be in here. Our stimulus strategy here is to enhance the UVM sequence mechanism to provide us with this low-level streaming. We're going to use high-level, user-friendly sequences that are easily combined to generate the scenarios we need. And ultimately, these will generate analog and digital data patterns that were required, such as the ones shown here. Yeah? We're going to use constrained random sequences to describe these shapes, but the driver is going to get a bit more responsibility to autonomously generate the derived low-level data values. Let's take a little look at the sequence execution. In general here, we're talking about standard UVM sequence operation with the high-level virtual sequencers orchestrating sequences on different physical sequencers, which result in an item being passed to the driver, and the driver has responsibility to drive that onto the interface signals that are connected to the device under test. The streaming data sequences are going to just extend this concept. The sequences still fully describe the stimulus behavior, but the autonomous driver will calculate all the derived low-level values. We have to make a modification to the sequencer driver handshake in order to provide a non-blocking handshake that allows the driver to run in the background. We found that this approach provides a much easier API for the sequences, which means that people using them higher up in the test bench layers can generate much more interesting scenarios without complicated forks and such like in their sequence layers. And most importantly, having introduced this non-blocking handshake, we also need to introduce a capability to interrupt at any time with new stimulus should it be required. Let's have a look now at the sequencer driver handshake. First of all, let's look at the normal handshake, which is generally used, where we get the item from the sequencer. We pass it on to a task that will drive all the values from this item to the interface signals, and when that's finished, we signal item done back to the sequencer. We're going to modify this slightly, as shown. Now, first thing to note here is that after getting the item from the sequencer, we're then going to signal item done back to the sequencer. This passes control back to the sequencer. And then we're going to drive the item inside a fork join loop. In this case, we have a blocking peak, which waits for a new item should it come along, running in parallel with the blocking task to drive the item. In this case, remember, the item could be driven forever, infinitely. And if the peak succeeds, then we will abort that and we'll kill the lower level threads from this drive item task. Let's look now at how we can generate real number analog stimulus using these techniques. Our goal is to provide high-level, user-friendly analog sequences that can be easily combined or used on their own to provide relevant stimulus patterns for the analog box. This enables validation of the complete system, the data path, and the interaction of the box with the digital subcomponents, but it also allows us to validate the integration of the models and the model behavior itself. Now, validating the analog model behavior in the digital simulation environment is important because these models become part of the environment that's used to sign off the device based on this digital simulation result. Let's consider, first of all, a simple analog ramp example. In this case, we have a sequence defined that's got some real and time control knobs for the parameters of the ramp. We're using real and time field utils and constraints here. Now, it could be that if your tool or license variant do not support these UVM extensions out of the box, then it's possible to use integral values with scaling factors. I'll show you that in the next slide. In other words, we've got a totally normal sequence structure. The only real difference at this level is we don't have the low-level details of all the individual steps. The driver will figure them out on its own. Now, the basic driver operation for producing the ramp looks a bit like this. Remember, the sequence item itself is describing the shape of the ramp without providing the low-level values. The driver can calculate these itself. As I mentioned before, if for whatever reason you're not using the real and the time variables types directly, then you can do the scaling here where we provide time step and precision values in the configuration object and just apply them this time. We prefer not to do this because it means the sequences and the sequence items are harder to read and a bit more error prone, so it's a bit more cleaner to propagate these values as real and time throughout the sequence layers. Analog signals have the additional complication that we may want to drive them as differential or single-ended signals when it comes to interacting with the device under test. We'd recommend you keep this complication out of your sequence layers and just apply it via configuration field right at the end as shown here. This means the sequence items, the shapes, all that kind of higher level abstraction doesn't care about how the signal is going to get driven, but when we get down to the very signal interface at the driver, we can choose whether to drive it differentially relative to some common mode reference or single-ended relative to ground. Now, to enable more advanced stimulus, we're going to replace the previous sequence item with the kind of structure that we're showing here. In this case, we've added a control knob to define the amount of repetition for the whole shape, and this can be an infinite number of times. We've also added an enumeration type to describe what kind of shape it is. So for instance, linear, sinusoidal, or file DPI. We talk about them later. And also there is an array of segment descriptors, each of which looks a little bit like the previous sequence item that we saw. These describe the pattern content for each segment. Now this means that we now have an array in the sequence item, we have an array of segments, each of which can be repeated a number of times. Another thing to notice here, that the segment descriptor content is generic. It will be interpreted based on the kind of shape. That might mean in some cases we ignore some or all of the fields, and in other cases we treat them as different values. For example, for the linear segment, the start and the step values and the rate are, as we mentioned before, for describing a ramp kind of effect. But if this was a sinusoid segment, then we care more about the starting phase, the ordinary and angular frequency, and the amplitude of the sinusoid. Now the driver operation is just a little bit more complicated than the last time. Obviously we have to handle all shape kinds, and for each segment in the shape we need to interpret them differently. But the inner loop here is not so different. We're still, in this case, the linear section, we're still calculating the low-level values based on the information supplied by the sequence item. The other main difference here is that in addition we want to be able to repeat the whole shape a specified number of times or possibly forever. Let's have a quick look now at how we could define a triangle sequence using this sequence item. In this case, the sequence fields describe the high-level characteristics of the pattern, so the low and high points, the characteristics of the up and the down ramp. And the body of the sequence can translate this into the sequence item segment parameters as shown in this case. Our end point for the analog stimulus is to provide somehow a comprehensive library of generic sequences that the user can combine to generate these patterns. For instance, if he wants to generate a glitch in the middle of a ramp, or ramp up to some oscillating value, or some combination of sequences as shown here. The mechanisms shown make this easy to do because in the body of the test, you can just call, for instance, the ramp sequence, only partially constrained here. At some point later, typically after running some other stimulus, you can then engage this triangle sequence, which has been set to run forever in the background until some other important point in this scenario comes along and the user wants to stop that by running a level sequence on the same sequencer. And this will, remember, cause an abort of the ongoing indefinite triangle sequence. I just want to briefly mention digital stimulus. In other words, how we apply these autonomous data streaming techniques to generate low-level logic and bit vector digital patterns. Note, this is in addition to any high-level transaction-based packet streaming protocol that you might have to run, which is outside the scope of this particular presentation. The goal, in the context of these complex sensor SoCs, is really to provide more control at the analog to digital interface. For instance, we have more control over adjacent samples that might be going into memory, or stress patterns for the DSP, or file-based data for the complete system. This is to enable us to do more effective validation of the digital subsystem and the data path itself. The sequence infrastructure is exactly the same as I showed for analog. The main difference is that the ADC output interface typically has to be slaved to some control signals that are generated by the state machines inside the DUT, for example, start or end of conversion. One effective enhancement we can add to our portfolio here is the capability to stream analog or digital data values directly from a file. These files could contain real-world application data or data generated by some external mathematical tool, for instance. And this enables us to create more realistic or complicated scenarios, such as the one shown here, just by a straightforward sequence call, provided the data is available, of course. The sequence definition for a case like this is pretty simple. But notice in this case we've only provided repetition and rate as control knobs in the sequence. We haven't provided the path variable for the file, and that's simply because it's a string type, so it can't be a random variable. And if we add that as part of the sequence API, then it limits the way the sequence can be used. So we prefer simple pragmatic solution of providing the path into the config and provide a helper method for setting it, which the user can just call at any time before running the file sequence. Now, the other important thing to note here is that in this case we're showing the analog data rate as a control knob, but if this was a digital sequence, as mentioned previously, the rate is probably controlled by the configuration and the internal state machines of the device under test. So it would take the data out of the file based on the internal end of conversion signals that are observed in the device. The driver operation, I won't go through this in too much detail, but really we just have, this is part of the drive item, part of the thing we saw earlier, so just based on the shape type of file, we just do something different to what we did before. In this case, we're using the system Verilab methods to open the file and extract the data. In this case, we're showing a mechanism where we're getting and driving just one value on demand from the file. We don't have to implement it like that, but if the files are massive, this might be a better solution. It also demonstrates one capability. We can do this in the driver, but in theory we could read all the file data in the sequence itself and pass it over as a big array. Even in our setup we could pass it as an array of segments. But if the file is very big, that becomes a bit inefficient, and also we can't really grab one value at a time in the sequence layer and pass it across. It becomes a big performance hit, assuming the data on the analog interface, for instance, is going at a very high rate, gigahertz, for instance, then that would be very inefficient. But in addition, this kind of approach here can be easily extended. We could have another fork in this case statement to handle DPI function calls using the same pattern, if you like, here. In that case, we would get the data from an external model, C, MATLAB, Python, something else. But we get the data using DPI function calls, and there we would also typically get the data on demand, only when we require it. Okay, let's now have a look at internal driving. In the case of our complex sensor, UVC, we're introducing this concept where not only do we drive the external interfaces and sensors, although we're driving an internal net, they are sensing external values, but we supplement that with the capability to drive internally analog nets. Typically we would bypass the analog chain, and also this capability that I mentioned before, driving the ADC digital outputs using these streaming techniques. This we found to be a very effective technique. It allows us, for instance, to develop the tests on this test bench in the absence of the analog model, so we can develop quite a lot of tests before the full path is there for all the analog models. And even in some projects, although we have a netlist that includes analog blocks, we may not have digital simulation models for the analog blocks. So this technique would allow us to bypass these blocks for the duration of the project. It also allows tests to be run independent of the analog models. So in other words, we can write tests that should behave correctly in theory with and without the analog models, and we can write two versions of the test to validate this. These tests we would typically hold on to for the duration. We would use them also at tape out, the two different styles of test there. Now, this approach also somehow helps us to validate the model behavior, or at least validate the digital behavior independently of the model. And that again is useful because these models become part of our digital sign-off. And last but not least, of course, it does provide more control at that digital interface as mentioned previously, which may be useful for stressing the DSP and the memory, for instance. Consider here that this top-level test bench is giving us the capability to run tests where we're injecting stimulus internally or externally. We don't need to dynamically swap between them. It's just different modes of using the test bench. And that allows us to make a simplification here because the UVCs themselves only drive the interface, and we can react to the interface to decide if we're going to drive the internal nets, because it's very important that if we're not driving an internal net, that it does not interfere, that the test bench does not interfere with the DUT behavior on that net. So here we're saying if the interface changes state, then we will force device-specific internal path to the interface value. Now we're doing this in the test bench, the module test bench level, not in the interface. The interface itself doesn't know about the device-specific path here, but inevitably somewhere in your test bench you care about these paths. So we're just doing it here, and we're also using the force procedural continuous assignment. But yeah, you maybe need to use, in some cases, the vendor-specific system functions to do the force. So for instance, if the target net is in a VHDL or some unsupported net type, complex net type, or I don't know, what a WREAL that is either isn't supported or isn't supported by your license, then you can use the vendor-specific functions to do the force. In conclusion then, I presented the concept of autonomous analog and digital data streaming using these high-level sequences that describe the pattern and low-level data generations handed over to the driver to do. We found this to be an elegant and pragmatic solution for various verification challenges, but especially in this domain of complex sensor devices. I've deliberately avoided talking about AMS, but clearly because we're using real number stimulus here, there is the scope for using this for analog mixed signal verification using UVM. I avoided using that term up to now because I don't want to lose the digital simulation audience for which the paper is primarily targeted at. The mechanisms we've shown you, of course, are straightforward modifications to your standard UVM, so they're relatively easy to implement, easy to use and portable, which allows you to focus on the high level, interesting and relevant scenarios, and it allows you to validate all these low level details relative to analog integration. Hope that helps you get some consistency in results for your verification challenges. Thank you.